another draft physics video presentation. A couple of videos. I'll do some piece of them anyway. Sean Carroll, Lawrence Krauss, and whatever his name is, Silence Asylum, whatever. Yeah, subjects. So this is, Sean Carroll's kind of a math guy, I guess you could say. And, lots of people try to define what mathematics is, and it's just kind of shortcuts. It's kind of making, like you say, an abacus is mathematics, or a slide rule is mathematics, in the sense that it's this mechanical device that allows you to figure out what, plus and minus left, how much did you go left and how much did you go right, and you can just eliminate the rights and the lefts, the plus and minuses, to come up with kind of straight line to explain something. But it's all kind of just a trick. And like if they do a computer simulation, or I just called it a computer simulation, if they try to calculate something in a computer, what they're often trying to do is just simulate it and then speed it up, because they can just average things out for, and turn 10 minutes into 1 second of processing time, is 10 minutes of the moon cycle or something. And so they can do some calculus, some math, some little tricks to do the, what happens every 10 minutes, where's the position. But the computer's really just seeing where the position is. It's doing an integral in a physical way. It's making a model of the moon, traveling, and it's just kind of, like I said, speeding it up. And so there's lots of tricks like that. Like, say, if you had you had a fence you were putting in, and you had to go around a couple of trees, and you wanted to put your fence in, you had to, I have to do this, and I have to do this, and then I make my fence. And you want to know, well, how much fence do I need, right? Well, you know that if you just draw a model, if I just do what I just did, you know that this distance is your original distance. You already got that, so that could be 40 feet or whatever. And you could just take a piece of string, just measure it, and then you could just compare the two strings, the straight line string to the string that actually accomplishes the task, and the difference in the length of those two strings will tell you exactly how much more fence you need. So it's sort of a trick, but it's not a very complicated trick. But that's really just math. It can save you, it'll add up these things and tell you how much extra you were off a straight line. I mean, it's not doing anything magical. And it's this kind of a synthetic way to understand something, but you don't really need to destroy fundamental ideas that that these are trees, and see, they want to pretend that they can turn force into nothing, as if it doesn't exist as a thing, because they're just going to count it as a quantity in a direction, and so they'll just say, well, this and plus this equals 0. But it doesn't really. It's this plus this. It's real energy. It's a real thing. It's not a 0. It's made of components of 1 and a component of 1. And the fact that they have opposite signs is significant, but it doesn't mean it's not there. It doesn't mean that's the same as no forces. I mean, this and this are not the same thing. And so it's kind of important to recognize that there's an actual functional thing that's creating the net number. So you got the same number, but they're not the same thing. And I've sort of drawn these analogies. I mean, just like the reflection can look just like the miss, in terms of something going this way and something going that way, and it can look like nothing at all. I mean, no energy at all or something, but they're not the same thing. All right. So, preface. I mean, the simple argument is that they are, as much as they say they have all this predictive power, their theories are, amazingly amazing in terms of what they've predicted in the world. They really haven't predicted anything. It was what the information already goes in before they can predict the outcome. So it's not like their mathematics actually creates any understanding of something that is. It's just the fact is that it's innate in the freaking outcome what the income is. I mean, you can dissect a cupcake and figure out what's in it, a flour, this, that, you can synthesize it and break it down and dissect it. So of course you can figure out what's in something. It's not going to be, it can be hidden, but it's not something can't be found out. So my simple argument is that they know that there's, in gravity, there's a force. I mean, there's a real thing because it travels a real speed. It's not any kind of instantaneous thing. We know it's the same stuff. All of it's traveling the speed of light. The speed of light is all over the place doing stuff. And we know that's got to be the answer. There's a mechanism. There's a stuff. There's not some bent space. There's not some invisible thing that's doing it. Invisible, wrong sense. Something that can't be qualified as actually being something that is the roots of energy. I mean, force is energy. And the key is that all you're looking for is an imbalance in the force. That is, you have, -2 and you only have a +1, and you have an imbalance, and the imbalance means that, this equation is going to mean that this is going to move. How else to say it? Because they're trying to say that, we can do all our math and all of our figuring, and we can just pretend those things aren't real, and that the only thing real is somehow the stuff that is, these locations in space. Well, of course, the locations in space are where you could do the same thing with photons. I could pretend there's no light bulb and calculate based on the fact that I know that every location in space, I know exactly how much of a photon is in every location. But why would I bother doing that? Wouldn't it be simpler to just understand that I know that there's a ray here, and I know there's a ray coming off of here, and I know there's a ray going this way? I mean, in my opinion, it seems the long way around, not the shortcut. The shortcut is recognizing that the forces are what makes things happen, and that they're straight lines. I mean, it's just so obvious. Anyway, so look, all there is in the universe, as I will contend, my prediction is that they will eventually realize that all there really is the force moving the speed of light, and the matter bits essentially collect momentum, and when they collect momentum, this doesn't get where it was going, which creates a negative state over here. Over here ends up being negative because this little positive bit stayed here instead of going there. And that's all there is. Everything functions based on this idea that you can take energy, force, and you can do this to it. You can force it to stay in this little block of space instead of going into the universe where it's supposed to be, or where it would have been. And that's all there is. There's just what is and what would have been. Alright. Sorry, it's all seeming quite tedious to have to go through this process of explaining why there's obvious flaws in this philosophy they have of science. Their philosophy of science is fundamentally flawed. And it can be seen in the fact that they can't agree on interpretations. They call them interpretations, right, of the two-slit or of quantum effect or whatever they say. And they have this Copenhagen thing and the many worlds and this and that. These are also their predictions. So they'll claim that we've so well predicted the, some kind of whatever, the weight of an electron or some kind of nonsense, which they didn't predict, but anyway, or calculate. And they clearly can't even agree on these simple, sort of what's the mechanism. I mean, the insane diversity of these opinions. Photons with radar, photons that do actually roll some kind of real dice. Photons that exist in many universes. These are bizarrely incompatible. And bizarrely extraordinary explanations for something we know has to be it's so consistent, it's so reliable, it's just it's just come on. These are extraordinary explanations, and again, I'll argue they have less than ordinary evidence. And there's no point in me saying this, but I've been saying this forever, and none of the defenders can admit the simple truth that they have very little evidence and they've drawn very hard conclusions. And the conclusions are not, they don't look right. They don't look complete at all. They're sort of just plainly nonsense. Many universes, I mean, come on. They look desperately silly.
Of this. And so it reflects this idea that there is a sense in which nature is lazy. Nature is trying to do the minimum thing. Here, nature...
Right, so they have this theory of least energy, or whatever it is, least action. And again, it's just, it's basically saying that you can always go to some default, and all you're looking for in analyzing a system is what forces are pushing on it. So if you know all the forces, then you can figure out how much they bent your straight line, or however you want to look at it. But anyway, there's no preference the universe has. It's just a mechanical fact that you can kind of figure out that if this doesn't get there, then there's probably going to be extra that over there. That the whole thing is going to come out to this one number. It's going to have some sort of equality in the system. And so you can kind of predict, like I said, if you have 5 heads, you're 5 heads ahead, eventually those 5 tails are going to show up.
Nature is minimizing the time it takes to go from where you emitted the light to where you absorbed it. Here, nature is minimizing this particular integral of the potential energy minus...
So in these diagrams, it was kind of horrible. I should probably have gone back and played some of that, but I just want to get to the point where he's basically saying, let's forget about reality and just play with our conceptual representations for reality. Kind of garbage. So he did the refraction thing, and yes, there's a way you can calculate it where you're saying because the light moves slower and blah 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 blah, but we know that the refraction isn't going to the fake location and then sending light from a fake location, so we know that's not happening. So why pretend that trick is the right answer? It's not the right answer. It's a nice little trick, but it's not the right answer.
The kinetic energy minus the potential energy. Yet another way of saying the same thing is...
So let's understand, potential energy isn't anything real. Potential is just, you're making just an argument. What's the likely pressure that's going to be on something? So I mean, I could say that something's going to just go from this point to this point. It's just going to, because of gravity, it's just going to fall down. Right? And then I could just start adding. But we know that there's a force here, okay, and it's traveling the speed of light, and it is going to intersect this as it falls, and it's going to apply a certain amount of force to the object moving it this way. And so, yeah, we have to know that ahead of time, that this is going to be another force. So it doesn't have just gravity doing this anymore. So there's not just one force. We know there's going to be another force, and then we can say there was another force over here. We can add a whole bunch of extra forces and figure out that this path is not going to be straight anymore, that it's going to go, because of these different interactions it's going to have, it's going to do this, and then it's going to do that, and then it's going to do this, and end up over here. Well, we know that these are real events, and we have to know about them before we can calculate them. We can't predict this is going to happen until we first know that that's going to happen. So the whole thing, there's no mystery here. It's just simpler to just draw the diagram and say, well, I know this force is going to hit, so I know this is going to go this way, and I know that's going to go that way, and I just draw the diagram, and I can take a piece of string, and I can just measure the distance difference, and what's the big deal? I'll know it's more time it's going to take because of the fact that 2 other forces acted on
it. Just think about, forget about light going through water and air. Think about light going through just empty space, right? We say it goes on a straight line, and you could think of that as not just light, but particles go on straight lines, etc. We think of that as momentum is conserved. There's momentum pointing in some direction, and it just keeps going in the same direction.
Right, unless another force acts on it. And their theory is, though, is that these forces act on each other when they already know from the gravity model that the forces don't interact, the forces just add or subtract.
But we also know that the straight line is the shortest distance path between 2 points. So we can think of the space of all possible ways that a ball or a light beam or anything like that could get from one point to another.
But the all possible ways just have to do with, we're saying it has to get here within a certain time. So we know in some cases we know it can't be a straight line because it's not going to get there in that specific time. So in some cases we can know that, well, it's supposed to get here in 10 seconds. It's supposed to get this line in 10 seconds. Well, we can know that this straight line doesn't work because it's only 8 seconds. So we know something else had to have interacted with it if it's going to get anywhere on this line in 10 seconds. And then we can just figure out, well, if the force can only come from one side, then we can also figure out that, oh, okay, it has to be somewhere on this line, and it won't be on this line. I mean, there's nothing magic about this. And just to deny the fact that we know the forces are what's going to change the line. You have to add something. There has to be something causing the effect. The effect isn't just something that happens and then you say later there must have been one. I mean, it's just a fact of every circumstance. It's not a simple enough way to say it.
The real physical one, in the absence of any forces, is the one that minimizes the path length. So the least action principle...
Yeah. So the least action principle is just this, like I said, it's just this sensible sense that I could draw all kinds of ways to get to this location, right? I could draw all kinds of squiggles going back and forth, almost an infinite number of them in some cases. But we know none of those things happened. So, why pretend that there's the most likely one versus all the ones that are very unlikely? It's not even that, there's rules to how much variation there could possibly be, because again, that would change the time. So again, there's no point in saying that over and over again. There can only be so much variation in terms of a jiggle. Like you either jiggled it all the way this way, you gave it one big jerk in one direction, or you give it a bunch of little jerks in both directions. But those are the limits to that equation. There's no way to go to Pluto and then come back. That couldn't have possibly happened. So, but they pretend that we can include all these other things because we don't care if there's an infinitely unlikelihood. It's another place where their math just allows, for no good reason, a bunch of infinities to exist that don't need to. But whatever.
Well, is a generalization of that, but the thing that is being minimized is the action rather than the path length. So the reason why it's a little bit tricky is because this is not the Newtonian Laplacian paradigm. This is not an initial value problem, okay? We're not saying, let's look at this diagram again. We're not saying I give you the position of velocity at the initial time and then chug forward one by one. I give you a piece of information now and a piece of information later, and I solve for everything that happens in between. And this...
And you can only solve for them, though, if you know of them. So the whole point, again, they're not magically predicting forces. They have to know them. So that's why they never solve any of these equations, because to solve them, they have to know all of these variables, and they don't know them. So there is no resolution, essentially. There's only a theoretical resolution that's still going to leave you with the same problem of you have to know what the forces are that went in the first place. You have to know that there was a total amount of 5 worth of jiggle, or whatever the thing is, to be able to narrow your prediction at all. Well, whatever. It's no point in me going over it. I mean, you can simulate it, and like I said, all of these circumstances, you could do it the easy way or you could do it the hard way, right? So if I'm putting the fence in and I got trees in the way, I can do it the hard way and do all this calculus crap to try to figure out how much displacement each tree did on my fence and how much extra fence I have to put in. Or I could just put a string along it and calculate, and use a model, an actual model, all right, and just do some measurements. So if you can draw a picture of it, then you can just use a ruler You don't need to do all of this complicated math.
This is completely equivalent to the Newtonian Laplacian way of doing things. So maybe Laplace just isn't the right way of thinking about it, right? Rather than saying, well,
Right, so this is where they just want to have this huge disconnect. So rather than thinking that there's actual energy in space, photons are actually moving towards us from other places. The energy is coming towards us, it's traveling. There's a real physical thing in a real physical location. It's in a location now. In a billion years, it's going to be in a new location, and that's a straight line. And no, instead of doing all that rational thinking, they want to do some sort of they want to abstract the universe into a bunch of notions that that aren't the truth, a fake model, and then start measuring and see how well that works out. Well, I don't think that's a good plan.
there's something that we know at the current time that implies everything about the future. Maybe there's something that we know about the past and the future that implies everything in between. And the answer is, it's either way. It's neither one of those is right or wrong. When we go back to the question that motivated us from the beginning of...
So this is, just the complete wishy-washy thing. Somehow we need to abstract the universe, and then he says, no, we don't. You can go do it either way. Well, I would argue that the rational way to do it is just to actually physically model it, and that's the safest way. Draw your line, and then just measure how long it is.
This video. Is force real? Is it fundamental? Is it necessary? What about energy? Is that real? Is that fundamental? Is that necessary? Neither one of these are real, fundamental, necessary in the strictest construal. But there's
so again, saying in the strictest sense, there's no such thing as reality. Blah 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 blah. Why do you need to even go there? Why are they going there? Why are they doing this to the universe? What's the point of speculating that somehow the force isn't necessary when you have to use it? You have to make it into something. You can't just pretend it doesn't exist. And you're basically just telling me it's easier to understand a photon coming towards me by understanding every single bit of space around the damn thing, instead of just understanding it's a ray of light that has a certain dimension, and that's it. It isn't going somewhere else. It isn't going all over the universe. I don't need to make it expand and then artificially contract it again back to the simple thing, because I already know that simple answer works.
There's another sense in which they clearly are real. Something can be not fundamental or necessary in the sense that there's a different way of talking in which that thing doesn't exist, and yet that thing is real, right? This table in front of me is real. Here it is. I'm touching it and putting things on it. If I want to talk about the quantum mechanical theory of the universe, this is just a little subfactor of the wave function of the universe, right? I would never talk about a table at the level of the quantum mechanical wave function of the universe, and yet here it is real. The same thing.
So I don't even know where he's going with that. I mean, even if you have a multiverse, you still have these individual universes, and they have individual structure, so why wouldn't I account for the fact that their table is different than non-table? I mean, something made out of wood is different than something made out of oxygen, and I can understand that if I put the table in space, that it's really different than the empty space.
Thing is true for things like forces and energies. These are ways of talking about things the universe does. The universe is real.
It's momentum, it's movement. Things move. And the rule is the forces move them. There, aren't we done? That the matter doesn't have any engines. It doesn't have any... It has engines. It just doesn't... It has seats. It's a boat. But it doesn't own any rowers. The rowers are the force. The force is what tells it where it's going.
At the fundamental level, I'm going to make a bold philosophical claim, and the philosophers watching can disagree in the comments. At a fundamental level, the universe is real in a way that nothing else is. None of the other words that we use to describe the universe quite have the level of reality that the universe itself does.
Well, I know this is but just getting into a picture's worth 1,000 words, or 1,000 words can describe a picture. I mean, it's just, it's kind of just doesn't go anywhere. There's a universe, and there's the easiest way to illustrate it is just draw a picture of it. I mean, but clearly we have words that don't have any reality in the sense that they're composites. They're made out of like 17 different kinds of other words. Like you could say wet, and wet is what? Well, sticky stuff, slick. You could start going through all the descriptions of what being wet is like.
So when you talk about things like energy and force, even position and momentum and things like that, those are useful ways for we human beings to describe the universe.
So they're useful ways. He's kind of implying they're not accurate. When, of course, they're accurate. So what's the problem with just doing it that way? Just recognizing that there's a mechanical structure. Now, the truth is they can't resolve the reality because they haven't correctly understood the function. So sort of like the Faraday mistake of confusing lines of force with field lines and thinking the field lines were force lines. You make mistakes like that, well then yes, you're going to have a problem drawing a model because there won't be any continuity. It won't make any sense because you're making things do things they can't do. You're making curved lines out of some sort of no force.
And useful isn't meant to mean just subjective and arbitrary. It really is a metric. It's a way of measuring how helpful things are to us because of the amount of information that this concept conveys. Remember, we said that force conveys a lot of information because it's a function of the positions and velocities of everything else. And from that function, you can figure out the acceleration, and that's all you need. Here, we don't use that. Force was not necessary. It was not built in an irreducible way to the fabric of reality. But we had a replacement for it, right? The action, the kinetic energy, the potential energy played.
Right, exactly right. So you summed it already. I mean, you can't say what its potential energy is until you've defined exactly what forces are going to act on it. So again, this is just, what's the point of pretending you've broken the need for causes for effects when you haven't? You're just pretending that because I've already summed a cause, I've already accounted for them and zeroed them, that somehow they never existed. And that's, again, just silly.
The role in the least action principle that force plays in Newton's laws. So the world is what exists. All of these words that we use to talk about it, all of these concepts we use can be very, very helpful. And if our motivation here is going forward, trying to improve our current understanding of the laws of physics, we have to be open to the possibility.
I don't think it's at all helpful to invent concepts like things being in one place and infinite gravity and nothing knows where it is, and uncertainty is something built into the object rather just a fact of our inability to perceive detail. Again, I could argue that, wow, that the screen I'm looking at is complete magic. Or I could take a magnifying glass and I could see its little pixels of light. I can know the truth, or I can pretend it's just magic. And, so I'm obviously opposed to the magic theory. Alright, enough of that one. I don't know if I want to do Krauss now. He's so irritating. Maybe we'll do some of this. So this is on the interpretations within quantum mechanics. So these are all the summations of why a photon essentially goes doesn't travel a straight line. So the question is, did a force act on it? Did it interact with something? Or is this something built into it that it creates this thing called a wave function? I don't know exactly how to explain what their interpretations are attempting to interpret, but let's play with it.
Wave function, and we still don't know. There are some that we've ruled out. Mm-hmm. We've ruled out a lot of what we call hidden variable interpretations.
Right. So the ones hidden variable interpretations would be the ones that the surfaces are actually causing the effect, just as the surface deflects light and cause it to refract inside transparent mediums. It happens at the surface. Likewise, if you travel this way, you'll go this way through the surface, you'll refract, right? You go this way through the surface, they're saying nothing happens, that can't possibly be an explanation. So there can't be any mechanical cause for the effect, they're saying, and they somehow ruled that out based on experiments involving spinning mirrors and polarizing film. Two things they don't understand at all, frankly.
Right.
And so those are ones where, like, well, no, those properties, the particles have those properties. We just don't. We just can't measure them for whatever reason.
Yeah. And people were clever enough to come up with, like, was it Bell's?
Bell, yeah.
I don't.
Joseph Bell, I think.
God, my memory is so bad. But yeah, people have come up with the most creative ways to rule out different theories on quantum mechanics. So
they're very creative, but she doesn't know how they work at all. They shouldn't know the mechanics of the experiments at all. So again, they just go back to some 1980s Allen aspect experiment with polarizing film. Like they understand how a polarizing film works. Like they can draw you a picture of that. Like they can't draw you a picture of the spinning mirror either in the experiment. How does the spinning mirror exactly create two equal beams of light? And all we can go through all these questions where they haven't done enough analysis of the experiment themselves to even understand how it works. Again, I could keep saying this about the interferometer. Half-silvered mirror is not going to create two equal beams of light. It can't. It's theoretically impossible.
I find this fascinating in and of itself, that like just the concept of interpretations, that you've got like quantum mechanics, which is a set of mathematical rules and principles that describe how the quantum world.
Right. So let's understand mathematical rules. The rule is that things happen, and if I create enough variables, they will look probabilistic. That is, I'm always randomizing what each variable is going to be doing. So if there's so much yin yang in the system, right? And I can't tell which little bit is going to yin and which bit is going to yang, But I do know through experiment that there's something confining how wide that probability can get. So I know there's a range of possibilities, and that they all can be assigned a value of which one comes out the most often. So I can roll dice and I can find out that rolling the dice does create a randomized result, and I'll get just as many snake eyes as I'll get boxcars over time. And that's all they do, is that's the reality. So all these experiments are confined. It's confined to what's on the dice. So, if I'm polishing glass or whatever I'm doing to affect something, I can only polish it within the range of those dice faces. I can't go beyond that. I can't put a 7 on one of the dice. I can't put 7 dots on any of the dice. All right, anyway.
A very, very small world works. But then there are interpretations of that, which I find to be a fascinating concept in and of itself. That like we have had to interpret what all that math means, because we can't conceive of it. Like we have to.
No, so anyway, so this all goes also to Heisenberg, right? This simple logical argument that what's confining us from understanding photons? The fact that we can't view them, that I can't videotape them, that there's no light I can shoot on a photon and reflect it back, and then I can watch what the photon does. So the photon remains in the dark, and I don't have a flashlight that has a small enough beam, so I can't see any photons. So because I can't see them, it means the photon isn't in one place doing one thing. It means it's like a magical little gremlin. It just pops into all kinds of spaces. But yes, they know their mathematics will confine that to some sort of limit. But the real fact is the photon really does travel a path. And what they're saying is when it travels near a slit, somehow that doesn't change its path any. That's supposed to be your expectation. That the photon goes right next to the slit and the photon that goes right through the middle of the slit, those two photons have the same probability of going crooked. That's their intuition here. That's their interpretation. And it's on its face. You're saying, why don't you try that first thing first? I mean, why don't you test to make sure the surface isn't different than the center? Because it seems logical that they would be different. They're different in water waves. We know the water molecule that goes through the center doesn't change its speed. There's absolutely no probability that the water molecule that goes through the center of an impediment will change its speed. We know there's 0 chance that it will do that. And we know that there's 100% chance that the one that's right on the surface, the water molecules that are running across the cement barrier, those water molecules, it's 100% certain that they're going to be slowed down. So water tells you there's no quantum effect. So why do you think the real universe has a quantum effect when you're doing the same experiment and you say you've somehow proven the slit doesn't matter whether the photon travels next to the surface? Do you think they've proven that? Do you really think they've proven that that variable couldn't have possibly caused the result? No, they certainly haven't. They've chosen woo physics. They weren't forced to go there.
Interpret it. We feel like it's almost like a translation. It is like an interpreter, like a translator into like concepts that we can understand, which is why there's interpretations like the many worlds. Or many, I think that's what it's called, many worlds or something like that, where like you open Schrodinger's cat, the box that Schrodinger's cat is in, and the cat's either alive or dead, but that interpretation says that it's not actually...
Yeah, no, that interpretation says is that for every instant of time, because there's all kinds of molecules in the box, there's all kinds of atoms interacting with each other, that the cat is in actually a trillion gazillion states. It's in 5,000 universes where it's dead and 10 million gazillion where it's alive. And I mean, it's just nonsense. It's just so childish. This is childish thinking.
It's not actually alive or dead when you open it. You actually create another universe where in one universe the cat is alive and the other cat is dead. And the thing is, interpretations like that are ruled out by doing tests.
Right.
That seems like a hard one to test if there's a second universe created in which you cannot wander and go test because you're in your own universe. So I don't know that I have a favorite interpretation. I have a least favorite, which is that one.
Right, I do. I don't like it either.
Yes, the God theory. That's just so obviously God of the gap, right? You have a gap in you can't possibly disprove it, so therefore it's somehow realistically true. So I can just make up anything. I can just have complete fantasies. I can put I can just make up anything and just start gluing legs on things and arms and make things into fake things that they aren't. And, it's just such obviously bad science.
Not a fan, but it's still around because people are still.
Because you can't rule it out.
But as a non.
You can't prove it because it's beyond the scope of evidence. We can't acquire any evidence. So again, we can't prove the invisible man unless there was some theory that the invisible man still was excreting some sort of radiation, and we somehow could someday invent a device that can detect the magical radiation that the invisible man produces. It's going to require some, interdimensional ray gun or something, some, view scope, the interdimensional view scope. What's our chances of inventing that?
Quantum physicist is somebody who's not at the level where like people are still duking it out. Like physicists are still coming up with ways to experiment and coming up with new theories. And those are people who have done a whole lot more studying and have gone a lot further in physics and specifically in quantum mechanics. So they still are. So
again, the evidence of that is what? So all of these physicists that are working at CERN and LIGO and presumably other wacky adventures in physics, and what are they producing? I haven't even seen a bottle of Tang come out of it yet. I mean, so the accidental science of going to the moon, where you had to actually do some science to actually get there and do all that kind of crap, and you invented some stuff, microwave ovens and shit, whatever. So accidental science does better than this on purpose, we found the Higgs boson that will never, ever, ever, it won't even feed a guppy. I mean, you're not going to make anything out of it. It will accomplish nothing. It will advance human technology and human understanding. Absolutely zero. Nothing. You'll get nothing for it. Absolutely nothing for it. So all of these guys getting paid a whole lot of money to find something that, frankly, I don't think even exists. And they get to just say, we've done it, because no one's going to be able to test whether they did it. You just have to take their word for it. So isn't that all very convenient? The scientist gets to just go, we did it, and there's no way to see if they did any such thing.
coming up with new theories and ways. Like how am I supposed to come up with a favorite interpretation besides just like what sounds nice to me?
I think that's really the sort of the spirit of the question, though.
Yeah, isn't that the spirit of your whole argument, though? Your argument is that you have this you have all this predictive power, and yet you can't predict, you can't figure out how a photon bends or why it bends. What good is this then? What good is all your quantum mechanics if you can't even explain something that simple? Oh, it went from point A to point B. Why? You can't explain it?
Yeah. What feels right to you?
Well, certainly not. Yeah, Sean Carroll, certainly not that one.
So again, this feels rights thing, and look, I've done a minor bit of study to know at least a little bit in the sense that what do you have to explain? Well, you have to explain how the multi-slit, the diffraction gradient, projects images. So you should be able to figure out that, well, I can't randomize the photons, because if I randomize the bending, I'm not going to be able to send an image, right? There's no way an image is going to stay coherent on random bending. The ones here have to be going somewhere different than the ones here if I'm going to be sending an image somewhere. There has to be a rule that allows those two to stay coherent to each other. They can't be made randomly incoherent or there won't be any image. So we can take Feynman's interpretation, we can throw that one out because it's clearly not random as the nature of the universe. The universe isn't doing this random entanglement, whatever bullshit thingy, where wave functions automatically randomize outputs. So, they can do the logical deduction, but they haven't done enough looking at what they're trying to match. So it's even like a magnet. You have to figure out, you say, well, what is a magnet, right? What is it doing? So you can figure out the north is repelling the north, the south is repelling the south, but the sides are really different. Right? The sides are doing something different than the ends of the magnet, so you can figure that part out. And so you figure out the different things you have to explain, and they don't even do that. They don't even make a list of all the stuff the thing does, and then try to figure out why it does it.
Here's the next question. Diana and Nick. Diana has 2 N's, by the way. That's the only time I'll be sassy, I promise. I'm thinking of becoming an astrophysicist or astronomer. I'm afraid I won't get a job after grad school. Shout out to Anne. And with 2 N's. Is it a risky degree and job to have?
Well, whatever. So they just, I hate these interaction things. So they have 5 million questions flying by. They get to just choose some randomly stupid question, and, who cares?
Yeah, it's tough to say. Because, I mean, it depends on...
astrophysicist or astronomer. Yeah, the thing is, like, if you're aiming to become an astrophysicist or astronomer, it's certainly not a risky degree. It's the degree that you want in order to be an astrophysicist or astronomer. If you want to go on and do something else, a lot of the skills are really, what's the word, like, commutative?
No, you either want to be a real teacher, like you have to go to a real school and be a real teacher and deal with the whole doing it over and over and over again and blah, 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 blah. Or you get to be a talking head, or you're so good at it, somebody's actually going to pay money hoping you're going to predict something brilliant that they can make even more money off of. Those 3 choices, in my opinion, suck. Making a living at science is like making a living at art. I mean, you have to sell your soul to make a living. That's really the only option. Sell your soul. No, I'll just sell my soul. And, no.
You can use them elsewhere.
Right.
A lot of the skills are transferable. Well, that seems like a good word.
That's a better word.
Yeah, they're really not. So, look, there's computer science. You do that, at least you have some hope of getting a job somewhere doing something. So you have to know how a computer works. And then on the side, you want to know how stars and galaxies work and all that crap. Well, you got to know that that's all performance art. All right? The scientists, the people actually doing any kind of science is like minuscule. So unless you think you're a star, you're not going to make any money.
To a lot of other fields, like you can go on into software engineering very easily because you have to learn programming in a lot of the classes you do. And if you're at a school where you don't learn software engineering, shame on that school because you have to learn to code for a lot of science and tech jobs nowadays.
Right. So why don't you just say, the science really isn't science anymore. It's just computer science, because that's the only job you can really get. And the rest of this stuff doesn't really matter anymore. And us physicists are proving it. We're proving it to you by the very fact that we can't settle on a simple interpretation, a simple rational explanation of why photons go in one way and they come out another way. We have to create multiverses and, you know, photons that can play dice, and then photons that have, you know, radar and, you know, all kinds of, you know, they're fully functional little battleships that have all sorts of detection capacity and all kinds of, you know, they can just turn their rudder and move any way they want. You know, bullshit theory.
Yeah, that's my answer.
I think it depends on, you know, what you're going for, because I know people who went and they got a degree because they thought it was gonna, you know, get them a good job, and then they were miserable the entire time they were going through, and then they're like, I don't even want a job in this. And so when I was going through undergrad, particularly, I made sure that...
Yeah, you'll end up with some job where you're like reading MRIs or something. Oh, yeah. Yuck.
That I was doing something that I was enjoying, so that if for whatever reason I didn't get a job in physics, I still kind of enjoyed the ride. That's not something I guess you want to do if you're doing a PhD. You kind of want to have a plan in place.
Yeah. What is your favorite computer language? Have you done much programming, Nick?
Yeah, so I majored in computer science before I switched to physics.
Oh, snap.
So I have a background, I guess you could say. But I did a lot of programming in high school.
Oh, that's cool. Yeah, you got a head start.
Yeah, and so like there was QBasic, which is, you know, the thing that everybody should start. Well, everybody did start on back in the day. I don't know if anyone uses it anymore. And then that went on, like, that was sophomore year, and then junior year was C++, and then senior year was Java, and so like I learned a lot of these things.
Yes. Hated it. I liked BASIC. Yeah, I like it. But anyway, they ruined it all with this object-oriented crap. Just so confining. Ugh. I have to have the menu look like that. Oh, I don't want that. Oh, and if I want to change it, though, I have to put a whole... I have to add 400 tons of crap, you know, to slow everything down, just to change the background. I hated programming. Anyway, keep it simple, stupid. Spaghetti code is the only code that's fun. You know, just jump. Go to. If, then, go to. That's it. That's the only phrase I want. You know, in the programming language. That's the only function I want. If, then, go to. Alright, anyway. Let's go somewhere else. Let's finish the Krauss thing and be done with this slop. So first he's doing the whole frickin' two spontaneous events aren't spontaneous events. And Einstein was so brilliant to figure out that two spontaneous events aren't spontaneous events because two lookers see it differently. Who cares how anybody sees anything? How you see it or when you see it, we know how that works. Why is this even a subject? It shouldn't even be a subject, this stupid nonsense of when you see something. When you see it is nothing to do with when it happened. We can know that. We are smart like that. It's like the nuclear bomb pictures, for fuck's sake. The bomb goes off, and it takes time, you know, for us to hear it. And then it takes time for us to actually feel it. Shit.
We're just like the people in Plato's cave who saw two-dimensional space and didn't realize it was part of a three-dimensional world. But we live in a four-dimensional space, and we now call it...
four-dimensional. We live in a four-dimensional space, and it's been proven by the four-dimensional space experiment that we never did. That's how we proved it.
Minkowski space in honor of Hermann Minkowski. The second great unification caused simply by the unification of electricity and magnetism. Space and time became unified.
Yeah, nonsense. Okay, space isn't anything, and time is also nothing. Okay, time is just how long it takes a photon to get from point A to point B. There, that's the end of that. Done.
Okay. Next, we jump ahead. Who's this? Feynman, of course. It's on my book over there, so if you bought it, you see the picture. Just occurred to me. Okay, what Feynman realized, and actually before him called Dirac, but Feynman sort of explained it in a way that people could, and Dirac couldn't talk to people, but is that when you unify, the next great development, of course, was quantum mechanics. It happened after relativity. And quantum mechanics says that at very small scale, strange things happen.
Right. So again, we know that things happen. Now, how strange they are, that's another word, right? I mean, why do we think it's strange? So we take some photons and we force them into a something. We send them into an obstacle course. And we're surprised that some of the photons fall off the course. You know, some of them do something silly because we put an impediment in their way. It never happens that if there's nothing in the photon's way that the photon ever falls down. It always does its little thing. So this is just about saying, how does something affect a photon? What affects it? Well, we know that hitting electrons changes them, so maybe that's the simple answer to the question. Are there any electrons near the slits? Well, there could be, huh? Could be.
Strange things. The world becomes really quite unintelligible in terms of common sense. Electrons could be doing many things at the same time, and perhaps the most important aspect of this.
All right, so this is taking Feynman even a step sillier, right? The stuff Feynman did just for the fun of it. Okay, this isn't something Feynman said was actually how the universe worked. He just said, look, mathematically, I can create an equation where the same electron has all the interactions in the universe, because I just keep time traveling it. You know, I can do that with the math. So it's a math trick purely. It has no relative connection to reality. It's not a theory of reality. But they're talking like it is. And like Feynman actually promoted it as some sort of real theory when he didn't.
Was that what became called the Heisenberg uncertainty principle, which is that there are certain quantities that I can never measure exactly in nature, certain combination of quantities. It's not a property of my measuring device, but rather a property of nature.
Right. He says it's not a property of the fact that I don't have the tools to see it. When, of course, that is true. So they just want to pretend that's not actually one of the facts. Well, one of the facts is the only place we see this crap is coincidentally the things we can't see. So the only thing that has Invisible Man powers are invisible men. I mean, it's so circular. You know, you're just saying, "Oh, you're thinking I'm too stupid I'm going to fall for this." That only the gremlins have gremlin powers. Oh, gee, what a surprise! I mean, it's just so bad. So the stuff we can't see, he's saying we can't see it not because we can't see it. No, because it won't allow us to see it. And it won't allow it to be measured. It somehow the universe is preventing us from seeing it. It's not just the fact that there's nothing smaller than photons, so I can't bounce something smaller off a photon. There's just nothing to see it with. I can't do it. I can't expose it to information, okay, and therefore allow it to create a footprint. I mean, I can't make a substance for which it's heavy enough to step into. All the stuff I make is heavier than the thing I'm asking to put a dent in it. The grains are too big, so I can't see its little footprints. It's like an ant can't leave a footprint in a bucket of sand because its foot is smaller than the grains of sand.
If I have a little small particle, I can know where it is at any given time with it's precisely as I can measure it, but then there's an uncertainty in knowing which direction and how fast it's going.
So that's not true either, right? You can only measure it one way. Crash it into an electron. So that's all you can do. And when you crash it into the electron, you can know where it was going and how fast it was going. It will tell you that, basically, because it's going to convey momentum.
Or I can know which direction and how fast it's going precisely, but then I won't know exactly where it is. The net effect of Heisenberg uncertainty principle.
So again, they can't do either one of those things. Like I said, they can only do one kind of measurement. The measurement is crash it into the wall. And when you crash it into the wall, it'll create a vector coming out the other side that is its momentum. So you can tell what direction it was going, and you can tell how much energy it had as a frequency, these different things. So there's nothing preventing that. But the trick is that we can't tell when a photon hits an electron. Unfortunately, the electron doesn't give us reliable information. The electron is in itself under its own tension, and it's going to go who knows which way based on what tension the electron's in. So it's the condition of the electron. It's how flat the wall is we're hitting. See, we can't see whether the wall's this way or the wall's this way or the wall's this way. So we can't see the wall. So we can't tell when it hits the wall what kind of surface it hit. So that's the catch. But theoretically, there'd be nothing wrong with it if we had nice flat electrons to bounce the photons into.
Is I'd like to say that the laws of physics on small scales are the same as corporate America or in Washington, and actually in this administration they're exactly the same. But in the upcoming one, because basically the law is if you can't see it, doesn't matter, anything goes. Okay, and so that means that things can happen on microscopic scales that violate what you would measure, otherwise called the laws of physics. But as long as you can't measure them, it's okay. In quantum mechanics, they're happening all the time, and that means that. And it was Feynman who first realized that this implied something interesting. It really implies that empty space.
So let's understand, though, that what I'm arguing here is simply that some of the things that Feynman stated, with time, we can figure out aren't true. That, again, a diffraction gradient isn't randomizing photons. So this idea that every photon, no matter where it goes, the probability isn't. It's like me saying if I throw the dice straight up in the air and they hit the floor, they're going to have a different probability curve than if I do bounce them off walls before they roll onto the ground. The fact is that it does matter what I'm exposing the dice to, whether or not the outcome will be randomized. That's sort of the simple argument. And so you can deduce that it isn't true that the dice actually are randomized by being thrown. It's still dependent on the environment, the circumstance of what you're doing to the dice, and that's all that's going to decide it. The causes are real. The forces in the universe are real. There's going to be real causes to every effect. I mean, that's all this comes down to. They just want to break the logic chain that it is actually banging into the surface that actually causes the dice to turn, and that they turn with different velocity because I threw them with different velocity, and so they'll turn a different amount and they'll have a different reading each time because I've subtly changed subtle little variables. The variables are dictating it. Again, they're saying the variables are irrelevant, and you can prove, I think, the variables are relevant.
Is a boiling, bubbling brew of virtual particles popping in and out of existence all the time. I mean, particles can't pop in and out of existence in the classical world because they violate energy. You create mass where there wasn't any mass. But you see, as long as they...
So there's absolutely no evidence for any of this stuff. And what there is evidence for is, as you know, sort of like, what's his name? I have to think for a while. I mean, the gravity guy, California, Susskind, Larry Susskind, sort of admits the antiparticle isn't a real thing. The disappearing into the space and popping out of the space, these aren't real things. These are just ways of accounting for the fact that if I kick an electron out of a system, then I've changed its potential. Now there's a positive hole. The electron was filling something. If I take it out, there's not a real thing left behind, but the vacancy is real. The very fact that there can be a particle there because there is a place to hold it. That there's some mechanism that's saying, I'm a holder, right? Because it was working. And you can make it work again by just popping another electron back in that spot. So the hole actually exists. So it's sort of just doing the left-right thing. If I shove something right, I know there's something left. Okay, there's more left now because I've changed the balance. How else to say it? But that has nothing to do with the universe consuming and then producing. That's not the state change that's real. The state change that's real is that if you take the electron out, the proton is saying, I can grab somebody new. That's all it's saying.
Disappear very quickly. Heisenberg says it's fine. And that's happening. And in fact, this is actually an actual calculation of the space inside of a proton. This was shown at the Nobel Prize ceremonies. I was there, actually, and it was the people who allowed that calculation to be performed.
Right, the space inside of a proton. Forget it, right? Oh, yeah, that's a real thing. I made the image, so therefore it must be a real simulation of a real thing. Yeah, well, that's probably enough right there, right? Yeah, that's enough. Ugh, this is all so depressing. So anyway, until the next time and such, I don't think there was really any comments worth 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 interacting with or reading or anything. Anyway, so till the next time, we'll just call it a day. Yeah.